We have this function f, which is the cosine plus the exponential, and we first need to calculate the Taylor polynomial of degree 3 around 0, and then we need to estimate an upper bound for the error if x is going to be all the time in this interval, in the interval minus 1/4, 1/4. Okay, so let's begin with the first one. The first one is very easy because we know the expansions of these functions up to third order. So the cosine of x is equal to 1 minus s squared divided by 2 plus this. There is no cubic term, so the next term is x4, so this is x3 when x goes to 0, right? And the exponential is equal to 1 plus x squared divided by 2 plus x cubed divided by 6 plus x cubed when x goes to 0. So if we add these two functions, right, we add these two expansions, then we have the expansion of the function f. And you can see here this and this term cancel, so we have 2 plus x plus x cubed divided by 6 plus x cubed. Okay, this is the expansion of the function f up to third order, so the polynomial of degree 3 around 0 is just this one, so 2 plus x cubed divided by 6, right? Okay, for the second part, we need the remainder 30x. That means that all the time that we've saved deriving the polynomial here is actually not really saved if we have to calculate the fourth derivative, right? Because we haven't calculated the previous ones. However, in this particular function, it's very easy to calculate the derivatives because the derivative of the cosine, the fourth derivative of the cosine, is equal to the cosine itself, right? The derivative of the cosine is minus the sine, and that of minus the sine is minus the cosine, okay? That of minus the cosine is the sine again, and that of the sine is the cosine. So every fourth derivative you recover the original function, right? And of course, the exponential, the derivative of the exponential is itself, so fourth derivatives of the exponential just keep the exponential. That means that the fourth derivative of f is f. So we can estimate this very easily, is f c, right, divided by 4 factorial, and here we have x to the 4, right? And now we need to find an upper bound of this. Remember, c is actually, it's actually theta x, okay? So let me just write here theta x. So theta x, okay? And theta is any number between 0 and 1. So actually, if x is going to be an arbitrary number, it can be an arbitrary number in minus 1/4, 1/4. So we have to find an upper bound for this function within this interval here. So let's do that first, right? So we have this function, okay, and assume that x is between minus 1/4 and 1/4. So what is this? What is an upper bound for this? But clearly, one upper bound of this is this, right? The absolute value of the sum is the sum of the absolute values, but the exponential is positive, so we don't need to write the absolute value. The absolute value of the cosine is smaller than or equal to 1, so this is smaller than or equal to 1. And the largest value that the exponential takes in this interval, since the exponential is an increasing function, is e1/4, right? So here's our upper bound, okay? Here's our upper bound. Actually, we could improve on that, but this is the upper bound we're going to use, right? We don't. It's reasonable because this number is 2. It's 2.7 something, so the fourth root output 2.7 something is not a big number, okay? Right. Then, so the error that we're making when x is in this interval, right? 1/4. It's going to be smaller than or equal to 1 plus e 1/4 divided by 24, which is 4 factorial, right? And times the absolute value of x to 4. But the absolute value of x to 4 is smaller than or equal to this, because it's any value. X can take any value in this interval, so the largest value it can take is 1/4. So actually what we have is this, the 4 root of e, and then 24 times 4 to 4, okay? And when we do this multiplication of numbers, we get something of the order of 3.7 times 10 to the minus 4. Right, so this is a small error here, what we have, right? So this is the answer to this question. If you evaluate this polynomial at any point within this interval, the largest error you make is smaller than this number here. Okay, so this is affecting the 4th decimal position, so that means that 3 decimal positions are exact for the evaluation of this function at any point within this interval -1, 4, 1, 4.